Okay, so the days family here, where we're introducing the third and final big function family that we study in Algebra 1, and that is the quadratics. You now are a little familiar with the word quadratic because you know it represents any polynomial degree 2, right? So any polynomial whose highest degree is degree 2 is considered a quadratic. So pretty much our studies for the rest of this semester are going to be focused on this particular family of functions and understanding their characteristics, their patterns, their graphs, how to identify them from tables, graphs, equations, how to solve them, and so forth. And we're going to kick that off by really getting some basic characteristics about the graphic. So this chapter 8 is primarily understanding the graph and the patterns in quadratics. And we're starting kind of with baby steps. The quadratic graphs can have lots of different sort of moving parts, more so than linear equations. There's different numbers that kind of affect it in different ways. So we're going to break that down a little bit and focus on kind of one aspect at a time. So in 8.1a, we're focusing on the impact that the leading coefficient, the coefficient that is attached to the degree 2 term, to the x squared term, what impact that has on the graphs, okay? But before we talk about the impact of A, let's actually talk about some of the just general characteristics of any quadratic. Okay, so the first thing we're going to talk about is something we call the parent quadratic function. Now, I haven't talked a whole lot about the parent function, but that is actually coming, and we're going to go back to linears and talk about the parent linears and talk about the parent exponentials as well, now that we've learned, all three families. So the parent quadratic, or any parent, let's back up. The parent function is basically the original, most basic version of the graph of that particular family, right? So, for example, I'll give you an example. For linear equations, what we call the parent is the y equals x, okay? That to us is the most basic version of a linear equation. It has just the minimum criteria, which is just an x to the first power, and it doesn't have really anything else, okay? And so that's the parent original line. Okay, if we graphed it, it would be a line that passes through the origin. It just has a slope of 1. It doesn't get simpler than that. Okay, so that's basically like the minimum criteria to be a line. And then every other line that you ever study could be considered kind of a transformation of this original. So sometimes I call these, I'm funny around, I call these the big papas, the OGs, the originals, right? So that you can think of the parent function as that original value, and then all of the other ones are some sort of transformation of that original parent, okay? So I gave you an example over here on the top corner of the linear parent. Quadratics have a parent function as well. The most basic version of a quadratic equation is y equals x squared. Or f of x equals x squared. We know that f of x and y are the same, right? So just the basic x squared. It doesn't get simpler than that. And that is the minimum requirement we need to be a quadratic, is to have that x to the second power. So if you had nothing else around it, just that x squared, that would be the most basic version of a quadratic, okay? The graphs of all other quadratics are basically transformations, okay? So every other quadratic that we're going to study can be considered a transformation, like, oh, it was translated, it was moved, it was stretched, it was flipped, but this is the original. So a lot of the times when we're talking about these graphs, we're going to compare them to the original parent function, which is in quadratics, the graph for x squared. Okay, so now that we've kind of gotten that out of the way, then let's introduce the graph of the quadratic. The graph of the quadratic is the parabola. Okay, that's what we call it. Just like a linear has a line that's a graph, exponentials have the exponential curve that opens on one side. The name for a graph is called the parabola, and you can see right here, just below it, it's this U-shaped curve. That is characteristic of a parabola. It's basically, it's got this U-shaped symmetrical curve that is either pointing upward or downward. Okay, so let's break this down just a little bit. First of all, the lowest point on a parabola that opens upward, or the highest point if it opens downward, that's called the vertex. Okay, so the vertex of our parabola for this one is right here. And it's essentially where the curve stops, changes direction, and starts returning back the way it came, right? So in this particular example, this parent quadratic, this is the parent right here you have in front of you, the original parabola. It is decreasing as you come from left to right. Remember, we read our graphs from left to right, just like we read English from left to right. So when we are kind of describing what's happening here, we're describing it as if we were coming from the left side and moving toward the right. So as we start on the left, this is decreasing, right? So you can see here it's going down, 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 and then boom, it hits that vertex. And that vertex is either the highest or the lowest point, depending on which way it's pointing. But it's that final point before it turns around, changes direction, and then starts going back up, right? So that point right there is really important, and usually in word problems, it has special meaning. It has, some special value in kind of real life scenarios most of the time. Okay, that's called a vertex. And if this were pointing downward, just as a side note, then the vertex would be up here. It would be that highest point. If it were pointing downward, sometimes the parabolas will point downward, and we'll talk about what causes that very soon. But for right now, you just know that the vertex is the highest or lowest point where the parabola changes direction. Okay? The vertex of the parent in particular is always at the origin. So later on, again, we're going to talk about things that can change our parabola. This particular parent that is right in front of us always has the vertex at the origin. That's true for the parent function. So understand that the graph that we're looking at right now is for this parent right here. Okay? So that vertex is always at the origin. It also has something that we call the axis of symmetry. So the vertical line, I'm over here now, right? So the vertical line that divides the parabola into two mirror images or symmetric parts, that's called the axis of symmetry. And a lot of times you're going to see me abbreviate that like that, so I don't have to write the whole thing, and you're welcome to do the same. Okay? But that axis of symmetry is this vertical line right here. You can see it kind of dashed, that splits your parabola right down the middle and creates two identical mirror images perhaps here. Okay? In the parent function, this axis of symmetry is always at x equals 0, or right on top of the y-axis. So the axis of symmetry will always pass through the vertex, first of all, and that's actually true even if it's not at the origin. Like wherever the vertex is, that's also, where the curve, let me show you what I mean. So even if my grid was over here and my parabola is off to the side, wherever this vertex is, my axis of symmetry also passes through there, because that vertex is always right in the middle of the curve. Okay, so later on, when our axis moves around, the vertex will always be on that axis of symmetry. But for the parent function, that axis of symmetry is at the y-axis where x is equal to 0. Okay? And a lot of times I'll abbreviate that as AOS for axis of symmetry, so just know that when you see that on the paper, that's what that means. Okay? So we really want to be able to just look at a parabola and tell some of those really important characteristics. We want to talk about, does it open upward or downward? Where's the axis of symmetry? Where's the vertex? And then we're going to do a little review, because we're also going to talk about the domain and the range. So let's start with a couple of practice problems. Let's start with number 1. It says identify characteristics of the quadratic function and its graph. So when I ask for this, I'm really going to want a total of 5 things. Okay? So write these down with me. Okay? First of all, number 1, I want you to tell me which direction it opens. Does it open upward or downward? Okay? I want you to tell me where is the axis of symmetry. And I want you to remember that the axis of symmetry is always going to be a vertical line for these guys. Okay? It's going to be a vertical line. In fact, since it's a vertical line, we know the equation of a vertical line is always x equals a number. So if you want to go ahead and write that in, x equals whatever, we'll fill that in a moment. I also want to know, where is the vertex? What's the ordered pair for the vertex of our parabola? Okay, so I'm going to want that. And then last but not least, I'm going to want you to tell me the domain and the range. That's right, you know you missed it. Okay, we want to be able to look at this and tell what is the set of all x values that are valid or that are part of this curve or this graph, and what are the set of our range, sorry, or y outputs. Okay, so let's get started. Let's do number 1. So first of all, pretty simple. Just by looking at it, you should be able to describe which way this opens. Does it open upward or does it open downward? And you can see that the ends are going, on both sides are going in the up direction here, so it's going to continue going up infinitely. So this is considered to be opening upward, like the parent function does, so that's cool. Okay, let's talk about the axis of symmetry. So the axis of symmetry would be where that vertical line lives that splits our parabola right down the middle perfectly. And I would venture to say that it's going to be that line right there. That seems to be exactly in the middle, and I can see that like I'm the same distance away from either side, no matter where I am. It's the same distance on one side as it is on the other. So I know that's the axis of symmetry. So this looks like to be at the line where x is equal to -1. Do not write -1 because I'm not going to give you credit for that. So listen carefully. The axis of symmetry is a line, and when I ask you for it, you need to give it to me as the equation of a line. It happens to be a vertical line, so it'll always be x equals instead of that y equals mx plus b. But you still need to give me the equation for the line. So x equals -1 is the proper correct answer for that. Okay, let's talk about the vertex. So the vertex is that point where the curve changes direction. Okay, at some point the curve stops, going upward or downward, hits that vertex, turns around, and starts going back the way it came. And in this particular case, and it also always lives on the axis of symmetry. So in fact, even before I go look for it, I should know that if my axis of symmetry was -1, then the x coordinate of my vertex also needs to be on that line, so it'll be -1. So those two things should always match. Keep that in mind. That's going to help you. Okay? So for my vertex, it should have an x coordinate of -1 because it should be on the axis of symmetry, and it is. And then all I need to do is find the y coordinate. So -1 is x. Looks like I'm going up 1 unit there, so it's going to be -1, +1. That's where my vertex is. Okay, those are some of the really key elements for this particular quadratic. And then the last thing is the domain and range. So I'll move these down since I wrote the equation there. I'll move that down just a little bit. Here's the good news, folks. So the good news is that all parabolas, unless they're in a context of a word problem, right, that'll change. But otherwise, all parabolas, if they're like this, just a graph kind of randomly out there, have a domain that is all real numbers. Now let's talk about why. Well, remember, the domain is the set of x values and that are, on this curve or valid. And the way that I see this curve widening. And even though it's going upward, it's also getting wider. It's going toward the left infinitely and toward the right. So I can see that if I just zoomed out and just saw what this kept doing up above, this would continue to expand in both directions, right? And it would really have the ability to encompass the entire number line of the x-axis. So it has no endpoint on the left side. It looks like it's just going to continue expanding and going on. And it has no endpoint on the right side. It looks like it's expanding and going on. And so that's why the domain is all real numbers. Now, if all of a sudden you're looking at a word problem, and it's in the context of somebody threw a ball, then that might be limited, It might make it that negatives don't make sense, or, there's numbers that don't make logical sense in that word problem. But if it's this kind of problem, then it's just all real numbers, okay? The range is a little bit different, okay? Because, we just decided the domain was all real numbers because it's expanded infinitely to the right and to the left here, okay? But when I look at the x-axis, I don't think it's x, I just kind of messed that up. But when I look along the y-axis for the range, and I ask myself, is this thing expanding both up and down? The answer is no, right? So this comes from up here, and there's an arrow, and then, it kind of goes down, goes down, goes down. It hits our vertex, right? So we did this a little bit ago, so it's coming down, 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 down. It hits a vertex, right, which is located at 1 here, and then it turns around and comes back up. And so even though it's going on infinitely, it's going infinitely in the positive direction in both sides, and it does not keep going down forever. So the range is a little different, right? When I think about what y values are valid here, the only y values that this curve will ever have are values that are either at that 1 or above. There's nothing below y equals 1 here, because that's where my vertex is located, and that's when the graph just turned around and came back, started going back up again. So our range is only y values that are greater than or equal to 1. And you actually did a few of these back when we talked about functions and domain and range. I threw a few quadratics in there. I was sneaky about it. And y'all did pretty good with that. So just remember doing those. The range will never be all real numbers for quadratics because of the nature of that curve and the fact that it's a U-shaped kind of shape. It's never going to expand both up and down, okay? It should always end up hitting some point, then turning around and going back. And then, for that reason, that vertex is always going to be the limiting factor on the range, okay? Let's try number 2. And in fact, if you'd like, I think this would be a great one to pause, try it out, and then you can unpause the video and see how you did, okay? So if you did that, let's talk about which direction this opens. So now you can see this one is pointing down in both the, on both ends here. It's pointing downward. So this is considered to be opening downward. It's like a frowny face. Always think about the positive, the opening upwards is like a smiley face, and the downwards looks like a frowny face. Okay. All right. So this opens downward, and then let's talk about the axis of symmetry. Okay. For the axis of symmetry, if I look to see where is the very, very center of this line and at what x coordinate that vertical line is at, I get that that is at x equals 3. Okay, it's right there down the middle of the parabola. That vertical line would live at x equals 3. Okay, and then the vertex should also live on that axis of symmetry. So it should be then this point right here where it changes direction. The x-coordinate should always match what I had the axis of symmetry as. And then really the question is, what's the y-coordinate here? Well, it looks like it's at 4. So our vertex is at 3, 4. So if you got those there, you are in great shape so far. That's where our vertex is located. And then last but not least, let's talk about domain. Okay, so the domain should be easy because the domain is always all real. All real numbers. It's a word problem. The range, however, talk about the range, right? This is a downward, so all of these y values are going to live, kind of down here. I've got all these outputs, and it's going to be all these y values below and all the way up to that 4. That 4 is where it stops, and then it turns back around and starts going back down, right? So all of our y outputs, every point on this curve will always live on y values or parts of the y-axis where y is less than or equal to that vertex of 4. Okay? So if you got those, then you are looking like you're in really good shape. So flip it over. Let's talk about the actual impact. Now that we know what characteristics we care about, let's talk about the impact of having a leading coefficient in front of the graph. So if we're graphing f of x equals ax squared, okay, and a is positive, so it says greater than 0, but we know that's just fancy for positive. Okay, so if a is positive, then what that changes, check it out. Okay, I want you to look at the graph here, and in fact, if you grab your graphing calculator, you can kind of play with this on your graphing calculator as well. So if you need a second, pause this and grab your calculator. So open your calculator, let's see what happens. So we're going to go to the y equals, and let's start off with just putting the parent function, because all of these descriptions that we talk about are going to really usually be based on comparing to the parent. So in that y1, we can put the parent function. Let's see what happens when we have a coefficient in front of this that is between 0 and 1. Okay, basically a decimal or a fraction, perhaps like a 0.5 here in front of the x squared. So this should graph, oh, wait, I did that incorrectly. Let's try that again. Just clear the line. Okay, so let's say we do 0.5 x squared there. Okay, so I have an a value here that is between 0 and 1. It's a half. Let's see how that compares to the original parent. So if I press graph here, there's a parent function in blue. Notice the red one is the one that has the 0.5 in front. So if you notice, let's talk about what changed and what didn't change. The vertex is at exactly the same location. The axis of symmetry is at exactly the same location. It's still opening upward. But having that 0.5 on the outside as a leading coefficient changed how wide our parabola was. In fact, it made it wider. If you want to play around with this, kind of pick something even smaller than 0.5, right? If we go down here, perhaps instead of 0.5, let's do 0.2. And see, well, what happens if we have 0.2 in front of that? It got even wider, right? So compared to the parent function, having a number between 0 and less than 1, right, a decimal or a fraction, as a leading coefficient, makes our parabola get a lot wider. Okay? Now, let's compare that. Let's see what happens if we have a number greater than 1 here. Because remember, x squared basically has a 1 in front of it, right? So we're not going to play with 1, because we already know what happens there. It's just a parent. What if we put like a 3 in front of this? Let's see what happens then. Okay, that's greater than 1. It's bigger than the parent. The parent is still the blue one here, but you can see right away that the parabola got narrower. Okay, it got narrower because we have greater than 1 as a leading coefficient. Okay, and again, you can mess around with this, put something maybe even larger, like a 7 here, and then graph it, and you're going to see it gets even narrower after that. Okay, so the moral of that is that that's the effect that that leading coefficient has. When A is positive, if you have an a value that is a decimal or a fraction between 0 and 1, then we call this a vertical shrink, that wider graph. We call it a vertical shrink. And in fact, the vocabulary I like to use even better than shrink, let's write that down because it's my preference. Instead of vertical shrink, compression. Okay, that's called a vertical compression. On the graph, that makes it look wider. Okay? That's the biggie. Okay? And then if that value of A is greater than 1, like the last ones we did, then we consider that a vertical stretch, and it makes our graph look narrower. Okay? Now, the whole stretch and compression piece of it, I'm going to give you a little bit more of a visual explanation when I see you in class, but this is the true lesson right here, okay? I'll give you a few pointers in class that will help you remember that if you need to, but here on the video, just make sure you write that down and you understand that when you have a leading coefficient between 0 and 1, that's a fraction or a decimal, for example, like number 4 here, we would expect that graph to get wider, what we call the vertical compression. And if it's a number greater than 1, then we expect the graph to look narrower and be a vertical stretch. Okay? So let's graph at least 1 or 2 of these and see that in action. So it says graph the function and then compare it to the parent. Okay, so first of all, let's graph the parent. Now, when I pull up a table of values, because this is what I can do on my graph, I can come here to y equals, the one that we're graphing right now is 5x squared. If I need to, I can pull up a table to come up with some ordered pairs, right? So the blue here are ordered pairs that are on my parent function, and then the red are points that are on my transform point, right? So, and you can see that symmetry even in the table, how the numbers start to kind of repeat again on the other side of the parabola. You get almost like a mirror image in the table itself. 16, 9, 4, 1, 0, 1, 4, 9, 16, right? So that's the parent function, just x squared. And then in the red, we have the 5x squared, okay? So that means that when we graph this, we have to be wise about our scaling. I think we're going to be safe putting in a scale of -4 to 4 here, but right here in the middle, I am thinking that we need to, this right here, I'm thinking that we need to go by bigger. So maybe let's go by 2s here. So this can be 2, 4, 6, 8, 10, then 12, 14, 16, 18, and 20. Okay? So, and then these can go by 1. So 1, 2, 3, and 4. -1, -2, okay. So if we go ahead and plot these, again, the parent had the vertex at the origin, and then 1 squared is 1, 2 squared is 4, 3 squared is 9, and then 4 squared is 16, and then -1 squared is still 1, -2 squared is 4, -3 squared is 9, -4 squared is 16. So that's why we have, because we're squaring, the negatives become positive again when we square. And so that's why it looks the way it looks. There's that. Okay, now let's graph the g of x function, which is the one that is that has a 5 in front of it, the one that right here. Okay, so what we're doing there is we're squaring, but then multiplying. Or you can pull it up from your table too, if that helps. You have your ordered pairs at 0, 5, 20, 45, right? But basically what's happening is after we're squaring, order of operations, we multiply by 5. So where 1 squared was 1, then 1 squared was 1 squared is 1 times 5 is 5. Where 2 squared is 4, 4 times 5 is 20. We're already up here. And now you can see why it's narrower, because it gets bigger faster. Same thing on the other side, -1 squared is 1, times 5 is 5, -2 squared is 4, 4 times 5 is 20. So, and then of course the vertex is still at the middle, because when you plug in a 0, you still get a 0. Okay, so there's our parabola, got a little wobbly there, but it's just this U-shaped curve. Okay. So how would we compare them? We would say that g of x, this is what I'd be looking for here, that g of x is a vertical stretch by a factor of 5. That's how I would describe it. Make sure you use the proper vocabulary. In this case, the proper vocabulary is to be a vertical stretch. Okay. Try number 4 and graphing p of x, and then you'll press play and you'll check it. So try graphing the parent as well as the mu function, and then describing the transform. Okay, so check your work on number 4. This is, what you should have done as far as points. When I did my graph, these were ordered pairs, so I was graphing 0.6, 2.4, 5.8, 9.6 as the ordered pairs. So compared to the parent, you can see it does get wider, but we describe that as a vertical compression. Okay, so when you write your description as to comparing it to the parent function, you'd be looking at this part right here that I'm going to be on the search for when I check the work, that p of x is a vertical compression by that factor of 0.6, which is your a value. So moral of the story, right, if a is greater than 1, then it's going to be narrower than the parent function, and we'll call that a vertical stretch. If the a value is between 0 and 1, then we're going to call that a vertical compression, and it's going to look wider when you graph it compared to the parent. All right, so then let's talk about what if a is not positive? What if a is negative, right? So a is less than 0 here. Basically just means that it's a negative function. And there's good news, folks. Not much changes, except there's one big change, but it's easy. All that it does is it basically flips it downward. You can already see that here on the left. On the right, on this graph that we have here. But if we go to our graphing calculator and just go back to y equals, and all we do is change the sign in front, right? So we do a negative x squared here, which is, actually, let's leave that x squared since that's our parent. We're still comparing to that guy. So we're going to leave that x squared. X squared, there it is. But then what we do is we use an a value here that is, instead of, for example, I don't know, just a 2, we do a -2. we already know, you and I, that a 2 should make this graph look narrower. But if we actually make it a negative, not only does it make it narrower, but look, it reflected it downward. And so that's the other huge idea. The sign on A is the one that decides whether your graph opens upward or downward. That's really important, okay? Notice the value of A didn't really, do anything different. If A is 2, it is a little narrower. We could see a more exaggerated version of that. If you like, we can put in a 6 here, right? -6. So we really would expect a much narrower graph, and it is much narrower, but it's opening downward because of the negative. So the sign by itself basically decides if your graph is going to open upward or downward. And then the number of A, the value of A, right? Then that decides how narrow or wide, or what we call vertical compression or vertical stretch, is affected. Okay, but the sign decides upward or downward. So that's the last big idea that I really want to get across to you guys. When the graph is negative, our graph opens downward. Okay, and if we back up a little bit, let's actually do a nicer job with our notes here and kind of qualify here that if it's positive, then our graph opens upward. Okay, so opens upward. So if A is positive, it opens upward. If A is negative, it opens downward. Then the value decides if it's a vertical stretch or a vertical shrink. Okay, so let's take a look at number 5 here. Number 5, we have -4x squared. So I want you to think about the fact that, that's going to do 2 different things. The negative, right, just the negative by itself is going to make this open downward. And then the 4 is greater than 1. So we would still expect this to be a vertical stretch by 4, by a factor of 4, okay? It's kind of cool that now you can look at the equation and know what's going to happen before we even create the graph. Of course, we're still going to create the graph. But if you understand what you're reading, what you're looking for, you can figure out what the changes and differences are going to be, or what characteristics are going to be for that graph before you even graph it, okay? So if it's negative, it opens downward. But the rest of it is basically the same idea. If it's between 0 and -1, meaning like a decimal or fraction, we're still looking at a vertical shrink or compression. That's a better word, I think, than the one that the book has. So the negative will make it reflect across the x-axis, or in other words, open downward. We call that a reflection across the x-axis when we want to be really formal about it. And then the actual number compresses. And then if it's less than -1, like -2, -4, -10, right, we're still then looking at a vertical stretch by that value, and still a reflection because of the negative. Okay, so those are the big deciding factors. So let's finish off with number 5 here. If we graph this one, let's see. Let's say, so that means 16. Okay, so I'm going to move, I'm going to really make most of my space. Since I can already tell this is negative and it's going to open downward, I'm actually going to capitalize on my space by making most of my graph in the bottom half here. So I'm going to position my axes like this. And I already know that this is going to just go by 1, so it's -1, -2, -3, -4. And then 1, 2, 4 on this side. Okay. Now we know that the parent function would still be going up. It would have a vertex. One squared is 1. One squared is -1, and so forth. So we know the parent would be up here pointing upward like that. But let's see what this one does when we graph it. Okay, so if we do x squared but then multiply by -4, well, we said it a minute ago, 1 squared is 1, but then we multiply by -4 and we go down to -4. And I think I'm going to count, which is going to fix, yeah, I think I'm actually going to count by 2 so I can fit this. So this will be -2, -4, -6, -8, -10. So I'll have to fix my parent in a moment, but that's okay. For that. Okay, so 1 squared is 1, but times -4 is -4, so we'll be down here. 2 squared is 4, times negative 4 is negative 16. We'd be over here. Okay, same thing on the other side. Negative 1 squared is 1, times negative 4 is negative 4. Negative 2 squared is 4, times negative 4 is negative 16. So this would be the new transformation of m of x, right here. That's m of x. And then my parent really shouldn't be there, because I still just see 2, so it should be there. And then 2, 4. So it should be a little wider just based on my scale. Not a big deal, but I just wanted you to see that. So definitely narrower because of the 4, definitely reflected across the x-axis because of the negative. So that's what the new function would be. And my description would be both of those things. So the negative causes a reflection across the x-axis. And the 4, so that's one transformation from the parent. The second transformation from the parent is that this is a vertical stretch, because it's narrower, by a factor. Okay, so we have a vertical stretch by a factor of 4 that made it narrower, and then the negative in front of that 4 made this reflect down across the x-axis. All right, and I think we're going to put a stop on this, and we're going to finish number 6 and our word problem in class tomorrow.